Started.
We are live.
Thank you. Good evening and welcome to this special lecture series of Vigyan Vidushi 2021. Today we have the first Bibha Chowdhuri Memorial Lecture. So before I introduce the speaker, let me give you a bit of a background for Dr. Bibha Chowdhuri. As some of you may have heard about her, some of you may not know who she was. So I thought it's a good time to introduce her and remind you about her work. So she was the first woman particle physicist of India. She did her MSc in University of Calcutta in 1936, and not surprisingly, she was the only woman in the class. During 6 years following her MSc, she worked with DM Bose at Bose Institute and did some fantastic work using photographic emulsion plates. Basically, they developed a new technique for determining the momenta of charged particles by track observation, and this actually led to the paved the way for discovery of pi mesons, which was done later by Powell. In 1945, she moved to England and she joined PMS Blackett in University of Manchester, started working for her PhD in extensive air showers in cosmic rays. She actually finished her PhD work in 49 and joined back in came back to India, joined TIFR. She was the first woman scientist, though she got her degree in 1952. She built the bubble chamber and the detector setup for air shower studies at TIFR. After that, she moved around a bit. She was in Calcutta and then she went back to France and also in Michigan State University and came back to India in 61. Thereafter, she started working in PRL projects on the air shower experiments at Kodaikanal Observatory for first few years, and then PRL's underground experiments at KGF, Kolar Goldfield Mines in Kolar. Again at PRL also she was the first woman scientist. And in 1976 she took retirement, and after that she worked in Kolkata with colleagues from SINP and the other institutes in Calcutta, and she remained an active researcher till her end, till 1991. In these later years, she worked on understanding nucleus-nucleus interaction at relativistic energies with an aim to get information about astrophysical and cosmic ray phenomena. Let me take a moment to talk about her real pioneering work, which she did in 38 to 44, which was the most challenging and has had a lot of impact. This work was published in a series of 4 Nature papers. Nature is a very, very prestigious journal, and she could write 4 papers at that time, working in India under very adverse conditions. So these experiments were carried out, as you can see from one of the papers, in the Himalayas, in the Sandakufu and Darjeeling at very high altitudes. And they used to put photographic plates, and she used to climb there on the back of the mule to collect the plates in every few days and so on. So she has worked under extremely challenging conditions, even for anybody and particularly for women. And later when she worked at Kolar Goldfield Mine, that was again at the depths of about 2 kilometers. So as I just mentioned, that a technique developed by them, that is by Bibha Chowdhuri and DM Bose, paved the way for discovery of pi meson, for which Professor Powell got Nobel Prize in 1950. And the role of Bibha Chowdhuri and DM Bose's work was acknowledged by Professor Powell later in 1959, saying that how their technique was very useful for him. For her accomplishment, I think is better summarized by the 2 people, S.C. Roy and Rajinder Singh, who also wrote her biography in a recent article in Physics News, that Bibha Chowdhuri belongs to the first generation of women scientists who began their research career in pre-independent India. Born more than 100 years ago, opting for a research career in physics, visiting England for further research, and working in 2 premier research institutes after her return to India were no small feats to accomplish. Unfortunately, she sort of faded into the limelight and not many people knew about her. In 2018, her biography was published by Rajinder Singh and Suprakash Roy with a book named Jewel Unearthed, Bibha Chowdhury. So, as I just mentioned, that no accolades came her way during her lifetime also, and she was quietly forgotten after she passed away. It's important to note, though, that throughout her life she remained unfazed by all the inattention, immersed in the pursuit of science, a very, very committed researcher. In order to bring the story of her inspiring life to the younger generations, the TIFR and TIFR Alumni Association have brought out the Indian edition of this biography. Just a few months back, the book was released, and this book is available. You can visit this webpage and place the order. It's noteworthy that two posthumous honors have been bestowed on her recently. In 2018, the International Astronomical Union named the yellow white dwarf star as Bibha, and in 2020, the Government of India declared a chair professorship in her name to be instituted in TIFR or PRL. It's good to know that a woman scientist who started the work almost 100 years back in very adverse conditions, did a very challenging work, has got certain recognition now. She was a very good teacher, a good mentor, and an extremely talented experimentalist. Some of her memories and the story of her life and the works are also available in the Physics News issue, which was brought out to bring as a commemorative Bibha Chowdhury issue. Again, these links will be available to you in your Moodle resource information, and I will also put it up in the chat later. This memorial lecture is a token tribute to her. Her life story is exemplary and inspirational to younger generations. I am indeed very honored to be the coordinator for this first Bibha Chowdhury Memorial Lecture. Today's speaker for this lecture is Professor Mahananda Dasgupta, and it's my pleasure and a privilege to introduce one of my closest friends and collaborator, Mahananda Dasgupta. Mahananda completed her PhD in 1992 from TIFR. She started her work in nuclear reactions as a graduate student, and hers was the first thesis from BRC TIFR Pelletron Accelerator Facility housed at TIFR. The VV 2021 students will make a virtual visit to this facility next week. She went to Australian National University as a visiting fellow and then continued working there. A fellow of the Australian Academy of Science and the American Physical Society, Mahananda is known internationally for her research on accelerator-based nuclear fusion and fission. She has received many awards and honors. Queen Elizabeth II Fellowship in 1998 by the Australian Research Council, the Posse Medal by the Australian Academy of Science for outstanding research in physics in Australia by an early career scientist, the Australian Institute of Physics Women in Physics lecturer, undertaking a nationwide lecture tour of Australia in 2004, and the prestigious Australian Laureate Fellowship from the Australian Research Council in 2011. She has served in many national and international committees, including the C12 Committee of the International Union of Pure and Applied Physics, IUPAC. In 2017, Mahananda, together with Professor Nalini Joshi from University of Sydney, initiated and developed the Mentoring and Guidance in Careers workshop for early career women and gender diverse researchers in science who are working in Australia. Following extremely positive feedback, it is now an annual workshop that explores the many facets of forging a career in science. The Vigyan Vidushi 2021 team is thankful to her for accepting the invitation to deliver the first Bibha Chowdhury Memorial Lecture in Vigyan Vidushi 2021 lecture series. Today, she will tell us about nuclear reactions spanning fundamental physics to applications. Over to you, Professor Mahananda. Mahananda, you are muted. Yeah.
And I will start. Okay, is that all clear? Can you hear me?
Yes,
Okay. And you can see the slides?
yes.
Okay. And only the slide, right? Not anything else. Okay. Well, thank you very much, Vandana. And it is indeed an honor for me to give this first Vibha Chowdhury Memorial Lecture. Um, I just remained awed by the achievements of Bibha Chowdhury. And I regret that when I was visiting VCC, which is next to Science Institute, in the late 80s, she would have been there and I didn't have a chance to meet her. That would have been amazing indeed. When I was reading about Bibha Chowdhury, I realized that at a personal level, there is a connection because her family was deeply influenced by Brahmo Samaj, which was a very progressive society where women's education was very important. And my grandmother and her mother came from that, were highly influenced by that society, which ran through our family as well. So I will talk about nuclear reactions, as Vandana said. But because you're mostly master's students in the audience, I thought I will start with the fact that I did not think I was going into research. I was wanting to go into Indian civil service after finishing my master's and sitting the exams. That was my plan. But then okay. But when I was in the first year of my master's degree at the University of Rajasthan in Jaipur, I got a visiting student research program fellowship to go to TIFR. And that was a turning point in my life and my career because for the first time, I encountered the excitement of research, the excitement of meeting top scientists and seeing facilities which were state of the art. And, and it was an electric atmosphere full of art objects, amazing um, place to be, to think and ponder, and among a very inspirational set of people. And that made me feel, oh, this is good fun. Maybe I should just do a PhD and then I will do something else. And that was the starting of my research career. Vandana also asked me to talk about my experiences as a woman scientist. And I start with this photograph of Dr. Bibha Chowdhury at an international conference in Italy in 1955. I don't have to tell you where is Bibha Chowdhury because there's only one female in a group of people. And things have changed somewhat, but not that much. It's changing slowly. So the challenges are that the number of women in physics is still not very large across the world. And as we heard, that Dr. Chowdhury became largely invisible to, to the scientist and to the society in, in general. And I believe a part of it is because of ingrained societal biases. And also, I was interested in reading one of the persons had written that Dr. Chaudhary was seen as a very tough person, but when this person actually worked with her, that was not the case, and she was a great teacher and a great supervisor. So there are societal biases against women who are strong and do something different from what the society expects. And that is also true for us as women. Um, and there is biased evolution of work which still continues today. And there's an amazing um, sort of work which is done by Cassidy Sugimoto, who is a computer scientist, a data scientist, and it's really worth looking at. But we make opportunities, and the opportunities come from the same fact that there are not enough women in physics. That means if you do good science and are good at communicating that science, it is you would be visible. And that's a great thing. So that means at a conference, if you gave a great talk and it was led by science, then people will remember and people will ask you to come again. And that's a great advantage for us at this point in time. There is also the fact that women generally would have very good interpersonal skills, which helps in building teams, in developing collaboration, because that's how most of the science is done in around the world nowadays. One of the things which helped me in my career is to have excellent mentors who encourage me to apply for fellowships, for promotions, whatever, because again, because of societal sort of ingrained biases, we feel, oh, I'm not good enough, I shouldn't be applying for this. But that's where mentors come into the picture. And I would encourage everyone to have a set of mentors. It need not be just one or two, it could be different people who you can model yourself after, and it can be men and women. So one of the biggest thing to not be invisible is to develop network, which will help visibility. And this is something that's what I feel as a woman in physics, that I have been fortunate to have had good mentors and have had good colleagues who have supported me, and it has and enabled me to do science. So why do a PhD and why one would choose research as a career? And I would say because it is a perfect avenue for someone who is curious around the world, about the world, and who likes solving problems. What better career to choose than a research career? And this cartoon illustrates that as a scientist or as a curious person, when you look at the world, you try to understand, wow, what's happening? You look at a glass of drink and you say, what is the evaporation rate? You look at some patterns and you think of some sequences. This is what the curiosity in us drives us towards. So it is a career which is driven by curiosity, passion, and excitement of doing science. And of course, there's a good measure of persistent, positive attitude and hard work. But the satisfaction of understanding and observe phenomena, once you get to it, is amazing. And that's what a PhD will tell us. It teaches us to do is to how to solve a problem which may not have an answer, and how to go about it. And that's why people who do a PhD and go into other areas, they not only do just go into research in a huge range of areas and do well, because we know how to go about solving problems. And with that, I think I'll go to the science part of my lecture, which is done. The results that I will show are mainly from the experiments me and my group and my colleagues have done at the Heavy Ion Accelerator facility in Canberra, in Australia. Canberra, by the way, is the capital of Australia, not Sydney or Melbourne. And it is the accelerator tower is it's seen here. And in there, what we do is a range of things, which is nuclear reactions, nuclear structure applications. I will concentrate on nuclear reactions today and how it is then applied. So nuclear physics is quite interesting in terms of it has three of the fundamental forces at work. And I'll concentrate on strong and electromagnetic today, which is because when two nuclei approach each other, nuclei are positively charged because of the protons in the nuclei. And therefore, they will feel a mutual Coulomb repulsion. And that is shown here as a function of separation between the two nuclei. And if I draw the potential energy, we see the repulsive Coulomb interaction increasing as the separation distance reduces. Then the strong force come into being when the two are almost touching, and that's a very strong attractive force potential, and arises fundamentally from the quark interaction of quarks inside each nucleon. But the nuclear potential is a construct which accounts for the many body interactions of protons and neutrons. Together, when we add the two together, then we see that there's a point of inflection in the potential, and the highest point is the barrier, which the two nuclei must overcome to feel the attractive nuclear part and fuse. So if we are going above, coming with an energy above this barrier, then it is just barrier passing. But of course, we know because of quantum mechanics, we can come even at energies below the barrier. And in that case, it will be tunneling through the barrier. And that leads to fusion of atomic nuclei. Great, that's what we learn, I think, still in our masters. Let's use this then and talk and see how this model fares when we compare them with experiments. So this is showing energy with respect to the barrier. And this is the cross section of fusion, which is related to tunneling probability. The measurements are shown here. The uncertainties of these measurements are smaller than the points in most cases, the size of the points. And the single barrier calculation is shown here. And it is a log scale. So we are very widely off if we use that simple model. This is a factor of 100, this blue bar, and clearly it is, the experiments are well above what the expectations are. And why is that the case? That simply comes about because when we talk about that simple potential, we assume these nuclei are just tennis balls with charges. But actually, that's not the case. Nuclei are many-body quantum systems, which means that they have quantum states. So there's the ground state and excited states. As a result, what happens is when the two nuclei approach each other, the system gets into a coherent superposition of all these possible states that the nuclei may be found. So that means it's like the Schrodinger's cat problem, that we can be in more than one state simultaneously. That means I have to describe the system as a superposition of all these possible states. When one does that, what happens is instead of the single potential barrier that we know and love from a simple model, actually is replaced by a distribution of barrier heights. And some barriers are lower than the original barrier, and some are higher in energy. And now you can see why one saw so much increased fusion cross-section or the probability of tunneling, because when one thought we are going below the barrier energy and tunneling, if there's a barrier which is lower than the original barrier, then it will simply be barrier passing. And that is what causes a large enhancement in fusion cross section because you are no longer tunneling but just passing. And as if I may remind you, the energy, the probability of tunneling is exponentially dependent on the energy with respect to the barrier. So the further down we go, we fall exponentially. And when we go above the barrier, the tunneling probability is close to 1. And that's what gives rise to all this increase in fusion cross section below the barrier that we see. Great, we say. Excellent, we understand that. So let's just calculate this. Therein lies a problem. And experiments are lead the way in these cases because the nuclei are strongly interacting many body quantum systems. And therefore, we cannot do calculations from first principles. Calculations from first principle can be done, for example, for electromagnetic interactions. But whenever there's strong interactions, those calculations are not possible. So there was an idea which came about that in fact, we could measure these barriers experimentally. There is a definite probability of encountering each of these barriers, and that depends on the superposition. But if we can make very precise measurements of fusion cross-section, we could figure this barrier distribution out.
Nanda?
Yes?
Sorry to interrupt you. Can you talk a bit loud because sometimes it's fading?
Okay, sure.
Thanks.
So this was the proposal in 1991 by a theoretician, Neil Rowley. And you notice that it means you have to take second derivative of experimental quantities. Vandana, is that better?
Yes, please.
Okay.
Yeah, thank you.
So we have to take second derivative. That means differences of experimental quantities. That's very, very challenging. That means we need very precise measurements. And that like uncertainties of 1% or lower. And that's what can be done using very new instruments and novel instruments and separators and techniques. And that is what we and our group developed in-house. And so starting from the whole concept of separators to actually making each detector. That is done by us, our group, and our students. So this enabled very precise measurements to be done, and one can take this second derivative, which allowed us to look at this distribution of barrier heights. So if you look at the energy of the barrier encountered and the probability of encountering the barrier is shown here. The blue points are the measurements. This is what would be expected if it was just a single barrier, the dotted line, but actually you can see that is not the case. And in this case, it is because the nucleus samarium-154 is a cigar-shaped nucleus, which is reflected in its quantum states, which look like that, the lowest quantum states. And the lowest barriers, in fact, are encountered when the nuclei are in this orientation. And you can see to touch, this is where the distance is largest. That means the Coulomb barrier is smaller compared with this orientation when the two nuclei have to come closer. And therefore, the Coulomb barrier will be higher because the separation distance is smaller. So it allowed us to understand the barrier energies, the probabilities, and how the structure and the quantum states affect the reactions and the fusion process. And this then affected physics in a range of areas, which is what I will go into now. So this is the background. It was done in the sort of late 90s, early 2000. And so now I use the fact that we know the barrier energies from experiments. We do not have to rely on calculations or models. And that opens up a whole range of um, new areas we could go into. So, one of the first is from the barrier distribution measurements, we understood when that is combined with fission measurements, we understood that when nuclei are coming in this orientation, they are more likely to stick together and form a new nucleus, which is the compound nucleus or the fused product. And remember, fusion is what is used for making the new elements. About 4 or 5 years later, earlier, if you remember, or some of you may remember, that the periodic table, there were 4 new elements were added to the periodic table. And those elements were made in the laboratory through fusion reactions. And in those fusion reactions, there was a deformed nucleus, which was used, and a calcium projectile. But you can choose the energies from the understanding that came about before. One could choose the energies so that they are more likely to come and stick in this orientation, where you're more likely to form a new nucleus compared with this orientation, which is the lower energy orientation, which is less likely to stick together. And the reason is very nicely depicted by the microscopic calculations done by Cedric Simonel, where if you see, these are actual calculations from like each nucleon is considered, and then you collide the nuclei, state of the art microscopic calculation, and you see that they sort of meet together but ultimately separate. So this orientation therefore does not allow you to stick together and make a compact object, which will lead to the new element or new nucleus. And indeed, the pleurovium, for example, was discovered in Dubna in 1998 in collisions of calcium-48 and plutonium-244, which is a deformed nucleus. So these understanding then rides on one another. You understand something, then you do the next step. And you do it better because of the understanding that came before. If I go to another regime now, which is if I know the barrier energy, combine that with experimental methods which allow me to go down to the tunneling regime, because now we know, initially we were thinking, oh, we are tunneling here, but because we now know, no, there are lower barriers present. So we are not tunneling unless we go at energies below the lowest barrier. So we go further down in energy and further down in energy till you're below the lowest barrier. And now you are tunneling. So this is oxygen and lead fusing. So basically tunneling because we have gone down so much below the barrier. So the superposition effects are in this regime. Now we go below the barrier, below the lowest barrier. And what we see is measured, is shown here. These are experimental fusion cross-section. You can see spanning 8 orders of magnitude. This is the level of measurements that is now possible. And what we saw was, this is the fusion cross-section as a function of energy below the barrier. And this was the expectation of the models, including superposition effect. And now the cross sections are, or the probability of tunneling is much lower than what was expected. And why would that be? And it turns out part of the reason is because of Pauli exclusion principle between nucleons of different nuclei. They cause the barrier to be wider. So if you didn't include Pauli exclusion, then this is what this is how the barrier shape is. If you include the Pauli exclusion, because if you remember, as we are going down in energy, the nuclei are sort of overlapping more and more. So there's more chance of the Pauli exclusion principle coming into the picture, and that effectively increases the width of the barrier, which means the tunneling probability will be lower. And that's a part of the explanation of what is seen. There is still another part which is still not fully explained, and we are continuing to work on that. I go to now reactions of very fragile nuclei, because this is related to the developments around the world where radioactive ion beam facilities are coming up. So one can now accelerate things like helium-6, which is like a halo nucleus, very, very fragile, breaks up very readily. And they are compared with stable beam measurements, something like lithium-7. But it turns out these nuclei themselves are very fragile. And the reason for that ultimately is because of very stable nature of alpha particles. So what happens when we make measurement of fusion cross sections for something like lithium-7 fusing with bismuth 209 in this case? Again, fusion cross section is a function of energy, but we know the barrier energy. So we can calculate exactly what the expectations would be. And these are the expected cross sections, and this is the measurement. We are well above the barrier now. And why would that be the case? It turns out it is because the alpha particle is so well bound that it really wants to remain as such. And as a result, these nuclei break up very readily. So yeah, this is the suppression in fusion that we see. There is now a similarity. When we are going to very light nuclei, the clustering of alpha, or the stable nature of alpha particles, determines the structure of nuclei like carbon, which forms the basis of life on Earth. And the reason why carbon is formed in the universe and the quantity of carbon-12, these are current areas of research. And before that, actually, this was a great problem, because you fuse protons, then you make helium, as it happens in the sun. But then the next step would be 2 helium nuclei would come together to form beryllium-8, but beryllium-8 would decay away. So you couldn't have made carbon. And that is when Fred Hoyle proposed that actually there must be 3 alphas coming together, and there must be a resonance in carbon-12 nucleus of the 3 alphas. And that's why one forms carbon-12 in quantities which are larger than expected, because it is a resonance reaction. So the clustering of alpha particles actually played a big role in our understanding of element formation in the universe. So we come back to carbon. So we understand from the reactions that are happening in lithium, and that how it interacts, the alpha clustering, how it dominates the reaction process. Then we develop models to understand the fusion cross-section, and that then affects reaction models of carbon interacting with other nuclei. And why am I highlighting carbon? Because so this is what I was talking about. The experiment we did was to look at the effect of clustering in reaction. Why am I highlighting carbon? Because carbon is one of the nuclei used for heavy ion cancer therapy. So in where there are very sensitive areas where the cancer is, or in children, then and you want to protect the organs around where the cancer is, then the best way to treat that is using heavy ions, because their range in the cancerous part or any material, for example, for that matter, is very well defined, unlike X-rays. And therefore, one uses protons or carbon. And there's a large facility in Germany where there is heavy ion therapy. Okay, so what happens? So a carbon nucleus, very, very high energy carbon nucleus, goes through the body. And 70% of the time, it's actually not reaching the cancer. It is doing a range of reactions, which are all nuclear reactions. So there are high energy nuclear reactions which happen as the beam slows down when it goes through the material. There are medium energy reactions, and then low energy reactions, which is what I've been talking about so far, near the barrier. So there is, again, a range of physics which needs to be understood and has been understood. So there is different reactions happen at high energy, then at medium energy and low energy. I was talking about fusion and breakup so far. And there are different models for different regimes because you can make different approximations. And it is the coupled channels model, which is telling us about superposition, and the barrier passing model is what I talked about. But before that, all these models come into the picture when one is designing heavy ion cancer therapy treatment. So the whole game now is to understand and model these reactions so as to reduce the damage to the surrounding organs or tissues. And one does simulations and compares them with experiment to know whether the modeling is correct or not. And when we look at that, for example, the alpha production probabilities in carbon reactions in going through protons, oxygen, aluminium, titanium. These are cross-section as a function of energy, and the dots are measurements, and these are the models in the market, the best models. And what we see is at low energies, their models fail to produce the alphas that were observed. And a part of that reason is likely to be that we do not consider clustering of alpha particles in our models. And the experiments that are being done and have been done inform these models so that we are better at modeling the reality that we observe in experiments. I thought I will end with what has been, because it is Bibha Chowdhury's memorial lecture, and she worked on cosmic rays and nuclear reactions, as Vandana was saying, in Nature paper in 1941, where the origin and nature of heavy ionizing particles on photographic plates which are exposed to cosmic rays. Very similar physics is happening when satellites go around the Earth, because there are solar protons and heavy ions, which are the cosmic rays. And the cosmic rays, galactic and anomalous cosmic rays, they are all bombarding the Earth. And the Earth's magnetic field traps the electrons and protons and heavy ions. And the satellites which go around go through this environment where there are protons and heavy ions and electrons. As a result, what happens is this ionizing radiation causes failure of satellite components. So there can be electronics and communications, whatever. And therefore, every satellite component which goes into a satellite has to be tested in its development phase for its robustness for ionizing radiation. And when we are talking about space travel, moon to Mars mission, we have to understand how ionizing radiation affects plants, humans, so it's biological samples as well as materials. And there's an effort worldwide to understand and mitigate the effect of ionizing radiation in space. So this could be developing new materials, developing new ways to sort of switch off communications, perhaps in the solar flare times. Anyway, there are a range of ways one works to reduce the damaging effects. But the fundamental physics which is happening is the same as when a carbon ion goes through our body for cancer treatment. Here, the ionizing radiation, which is protons and heavy ions, go through a material. And again, the same physics is happening. So we have to model how, depending on the size of the satellite, how we go from high energy reactions to medium energy and low energy, all nuclear reactions happening all along. So this is, again, an area where my colleagues are advancing, and we will start building a beamline to understand these reactions and develop new materials. So I'll finish here. I think I've stuck to my time. So that what I hope I have done is to give you a glimpse of nuclear reaction dynamics at energies near the barrier. Because they're near the barrier, they're extremely gentle collisions of many body quantum systems, and they are determined by coherent quantum superposition, and the tunneling is affected by that. Something which I didn't go into, and which is again area of research, current area of research, is in this quantum many body system, we still see effects of energy dissipation. So the great question is, how do I understand energy dissipation, which is a classical concept, in a purely quantum system? And that is not just in nuclear physics, in other areas of physics, it is a current question. So I've shown that by doing precision measurement and comprehensive measurements, we develop new understanding of the underlying physics, which then affects a range of areas. So I talked about cancer therapy, satellites, light ion reactions, super heavy element formation. And as the new experiments come in and the precision increases, there are new theoretical models which are needed to match the latest result. They then enable prediction, which then affects applications of nuclear reactions. With that, I'll stop.
Thank you, Mananda, for really a very nice talk. You talked about 8 orders of magnitudes in the cross section, but I think you also have covered a wide order of magnitude range of the topics, and we will now take few questions. And it really was very, very interesting. And it's special thanks for sharing your personal experience and the advice to the students. I'm sure it will be very, very useful for our participants. So before I move on to questions, I will first take few questions from Zoom, but there are also some questions on YouTube, but there are few comments in YouTube, and there are several of your friends who are present there. So I will just say a few, pass on first few comments to you. So there are two comments of very personal nature. One from Malvika Gupta, your Didi. She says it's very nice listening to you, giving a seminar. And there's one from Pramod Bhagwat, who says it was nice to see the Australian Peloton, and remembers David Weiser, who has been your colleague as well as his colleague. Yeah. Of course, many people have appreciated the talk. So let me first take a question from students. So one of them asked, is the fusion cross section the only experiment that lead to the inference of many body problem?
No. One can talk about Bose-Einstein condensates and a range of areas like that. Cold atoms, very similar physics. The advantage of nuclear physics or nuclear reactions is nuclei are extremely isolated quantum systems. So in the case of atoms, you can shine a laser, you can increase the temperature, decrease the temperature, and they will affect the system. Whereas all our theories are for isolated quantum systems. Now, in the case of nuclei, you can increase the temperature to what you like. You can increase the pressure to what you like. It would not affect the nuclei. And we know that, and that's the reason we use nuclei as a clock running for billions of years to measure the age of Earth, for example. So anyway, so they're isolated quantum system. We cannot readily do anything to them. Nuclear collisions are the only system that I know where you can, basically when you look at the fusion barriers, it is essentially you are looking at the eigenstates or eigenbarriers, eigenenergies of the quantum system. There is no place, no other area where you can get a snapshot of the eigenenergies and eigenstates. We are able to do that because it is an isolated quantum system. So that is the beauty of nuclear collisions.
Thank you. We move on to the next question. What would be the number of barriers for any nucleus? Does it depend on its size?
It doesn't depend on its size as much as it depends on its quantum states. So if, for example, if it's an alpha particle fusing with another alpha particle, the energies of the first excited state of the alpha particle is so large that it's not easy to go into a superposition of that excited state and the ground state. So it would not affect the fusion cross section in that case. Your single barrier will be as good as the superpositional state, because basically we can write a superposition, but the other the coefficient multiplying the other wave function will be pretty close to zero. But if you look at something like uranium, which is the other end of the scale, the lowest state is few tenths of a keV, kilo electron volt, whereas you're coming with energies of million electron volts. So it's very easy to excite the lowest states, and therefore in that case it will make a big difference. I can see you can think, oh, it is size. It is not size, it is basically the energies of the states.
Thank you. There's a very interesting question. Why is that beryllium 8 is unstable and carbon 12 becomes stable due to resonance? Can you explain?
Very, very interesting. No, it's not that. Okay, again, if you delve down deeper and deeper, it'll come about from the many body interactions. But if I look at it simply as the picture that I presented, you cannot see why that would be the case.
Okay.
And in
Um,
fact, it's very, very interesting, that the 3 alpha state of carbon, they were, there was at one point about 15 or so years ago, all the computers in the US were harnessed together to put 12 nucleons together and calculate the states of carbon 12. And you can reproduce all the states except for the state which is the 3 alpha particle resonance state. And the reason is because the clustered, it's a it's a result of clustering, not the single particle nucleons being put together. So it's really fascinating. It's
yeah.
fascinating that we do not understand all the decay modes of carbon 12. There is a recent paper like 3 weeks ago, right?
So there is a comment on it, so which I will just read out if on the YouTube, if you may permit me, from Professor Vivek Datar, that in case of 12 carbon, two resonances get involved. So of course the ground state was known, beryllium ground state was known, and also the Hoyle prediction of the three states which you mentioned. So as you said, it's not coming out of the simple picture, but there are more complex things going on. So we move on to the next question now, which is. I hope I understand this correctly. What has been done regarding the dissipation of energy problems so far? I hope the person means
Um,
it's an energy dissipation in nuclear reaction.
hmm. So far, it has been very separated. Near the barrier, we only talk about quantum mechanics. Well above the barrier for heavy nuclei, we only talk of classical models. Clearly, there is no one standing there with a dividing ruler saying, okay, now below this, go quantum, above that, go classical. Clearly, that's not the case. So we are trying to understand that how to model the entire part. There are models, for example, in quantum computing areas, which model developments where you try to understand how classical nature comes out from a quantum system. And that is essentially from external perturbation. But in the case of nuclei, that is not there. So how do we understand that? We don't have an answer, we don't have a model. We have measurements which show that even below the barrier, we are seeing energy dissipative effects. And that is a publication from a student, from one of our postdocs this year, actually. There are models being developed where you include friction in quantum models. Microscopic models are being right now developed. We don't know the answer. It'll be great when we do.
Thanks, Nanda. We'll move on to next questions. We are also getting advanced in time, so I will take two more questions, and I want to tell the students that they can still type in questions both in the Zoom chat and YouTube chat. The questions which we would not be able to take now will be passed on to the speaker, and we will also make her email address available to you in the Moodle to all the students, Zoom and the YouTube students. She has kindly agreed to respond to questions. So I'll take first a physics question, and then there is an interesting non-physics question which I'll take. So first question is, even the distribution of static barriers is an approximation. Can we do better and do a truly dynamical calculation?
Yes. So the microscopic calculation that I was showing is essentially a dynamical calculation. The part which is missing in some of those calculations is how to include tunneling, because it's a mean field approximation and you can't include tunneling. There are efforts being made in that direction. So yes, this is what I didn't think I would have the time to go into. The computational advances are allowing us to get into that regime. And the movie that I showed is actually microscopic calculation.
As you can see, guess this was from an expert in the field. Uh, this is the last question, and I really like this question. I think it's very apt for this school. So this is from a student. There are many branches of physics. Which idea or which curiosity gave you an idea to work in the nuclear field?
It's the most silliest thing. When I was in my um, um, year 11, I had an excellent physics teacher, like superb. And they talked about nuclear reactions. And they talked about how you can change one element into another. And that was the most amazing thing to me because I had never even thought about it. Because we knew about chemistry. I don't make new elements because you start with some certain elements, you end up with certain elements, right? The same ones. Just that fact that, wow, you can create new elements from something different was stunning. And that's what made me quite excited. And then, of course, that perhaps unconsciously or subconsciously formed the basis of me choosing to join the nuclear reactions group at Tata Institute as a visiting student. And uh, the rest, as they say, is history. So
So thank you very much, Mananda, for once again for the very wonderful talk and a very lively question answer session. You also kept very much to the time. So I thank all the students and participants both on Zoom and YouTube for joining this first Bibha Chowdhury Memorial Lecture. And we'll say goodbye to the speaker now. We hope to see all of you back in our next special lecture, which will happen on 7th June, which will be given by Professor Nandini Trivedi. And of course, for all the Zoom participants and VV 2021 participants, the next session at 6 o'clock. See you all there.
well, thank you very much,
Thank you,
Vandana, for the invitation, and it has been a pleasure. I wish I could see all the faces in the audience. It's very hard to give talks when we don't see whether people are following. But from the questions, it seems that they were. I really enjoyed the questions. Yeah, thank you.
Thank you. Lots of them have expressed their appreciation. Thank you both on the YouTube and Zoom. And on YouTube, there are a few people who have also said nice talk. I must tell you, Amit Roy is there, Vivek Datar is there. So one of your mentors is there. I should, if I can say so. Yeah. All right. Thanks, Nanda.
Okay, thank you. Bye. Good night.
Yeah, yes.